Okay, so just now what we have talked now is about your uh, differences between heat and temperature. Okay, so Bhavok also has joined. Okay, now say. So what are we going to study in this chapter, right? So what is heat actually, or what does heat do? Okay, heat is related to energy, and since it is a form of energy, right? Heat, when a matter, okay, I'm repeating again, when a matter has heat, when a matter has heat, it means it has energy, and obviously, right, matter is going to use that energy. Okay, it's not just going to keep it with itself, it's going to use that energy. Okay, if I simply go to your gases, okay, you know what happens, right? Okay, in solids also, liquids also, gases also, when Joshna also wants to join, but where is she? Okay, so when a matter has heat, right, it means it has energy. And what can matter do with this heat? Let me just show you. Okay, the most simplest thing the matter can do with this heat energy is what? Can anybody tell me? How does matter uses this heat? Let it be solid, liquids, or gases. Imagine matter having energy or heat energy, thermal energy. Yes, yes, waiting. Imagine I have gases. We give him heat energy. Okay, Q. What do you think is going to happen to the gases? Will its motion be remaining the same, or
They'll get excited.
will get excited? Okay, the motion is going to be changing. Okay, motion will change. Okay, when I speak of motion here, okay, see how to talk about motion for these cases. Okay, see, we have basically three different kind of motion that we can talk about. One is translational motion. I think that makes sense, right? Translational. You know what's the meaning of translational, no? To go from one point, if the particle or the matter is moving to the another point A to B, right? We say such motion is what motion? Translational motion. Okay, if it goes from one point to another point. Another thing, this matter can use up energies to vibrate. Okay, it can also happen. Okay, solids, I think you have heard about this, right? If you have a long chain of molecules,
Yes.
okay, if you have a long chain of molecules or atoms in a solid, and you give them more heat energy, what will happen? They will just stay in one place, or they will vibrate more and more.
They will
They'll
vibrate.
vibrate. Okay, this is going to go left and right. Okay, but will not, overall the mean position remains the same, but it's going to undergo vibration. That's how solid can use temperature, or the heat energy they gain, okay, to vibrate more. Okay, one more type of motion is there. Okay, that is what? Translational, then vibrational, and what motion, guys? Rotational. Okay, so we have translational, motion, we have vibrational motion, and we also have another kind of motion I told just now, that is rotational. Okay, so three kinds of motion is possible for matter when they have certain amount of energy in the form of heat. Okay, so that's the first thing, and then let's just go straight forward. Okay, can you tell me some units of heat energy? Units of heat. Heat is energy only, so you guys can speak some units, but I want to know some new names. Okay, yes, waiting guys. Start. Yes, waiting. Unit of heat.
Joules, sir.
So
Joules.
joules.
That's the first one. Then SI
Kilowatt
unit.
hours, sir.
Ergs also correct. Whatever you said is also correct. Kilowatt hour is also correct. Very good. What else?
So calorie.
Calories is also correct. Okay, calorie is very nice. Okay, we have calories also. Okay, there's a definition, very nice definition of calorie. Okay, I'll just quickly tell you. This is important. Okay, definition of 1 calorie. Look at this. Okay, 1 calorie is the amount of heat energy required to raise the temperature of 1 gram of water from a temperature of 14.5 degrees Celsius till a temperature of 15.5 degrees Celsius. That means through 1 degree. Okay, through 1 degree Celsius. Okay, it is always measured in this range. Okay, between 14.5, you keep water, which is only 1 gram, and then what do? You make the temperature go up by how much? 15.5, that is by 1 degree. Okay, so the point is, what do you think? Can the temperature just rise, or it has to absorb heat energy, guys? Water.
Absorb heat.
It has to absorb. Okay, 1 gram of water has to absorb how much heat energy? Whatever amount of heat energy it has to absorb, right? We are going to call it what? We are going to call it 1 calories. Can you understand? I'm repeating again. Okay, look here. We have a container. Here I keep only 1 gram of water. Only 1 gram of water. And you ask yourself, can the temperature from 14.5 degrees Celsius change to 15.5 degrees Celsius? Yes, that can happen, right? Okay. So temperature has changed by only 1 degree Celsius. There's a rise in temperature for 1 gram of water, only water I'm talking about. So the amount of energy that's going to come and do this, right? That energy we call it as what? 1 calorie. So that is what 1 calorie can do. Can you understand, guys? Did you understand, guys? What is 1 calories? Yes.
Yes, sir.
What
Yes,
can
sir.
okay? So if I just ask you, what can 1 calorie do?
Yes.
Your answer is it can raise the temperature of 1 gram of water from through 1 degree Celsius, that is from 14.5 to 15.5 degrees Celsius. Okay, there are bigger units of heat also. We can call it kilocalorie. Okay, we can call it kilojoules and other things also we can bring. Okay, then let's go to temperature. Okay, very easily we can talk about temperature because already you have some idea. Okay, so temperature units. Can you tell me units of temperature that we can use?
Kelvin,
Kelvin, sir.
Kelvin
degree
scale.
Celsius,
Very
Kelvin,
good. Degree
Celsius and
Celsius.
Fahrenheit.
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 Okay, let me check the spelling. Okay, what's the spelling of Fahrenheit?
Fahrenheit. Height.
Heigt, no?
No,
No,
sir.
sir.
Height.
Mm,Heit. Here they have written Ghit, right?Heit. Fahrenheit. This one, no, I think. Fahrenheit.
Yes, sir.
Okay, so these are the 3 different scales. Okay, now you have to understand. Okay, degree Celsius. What do you think is the importance of degree Celsius? It's a scale, of course, but this is the scale, no? If I go up, it means high temperature. If I go low, below, right? Less temperature. Okay, so this is your degree Celsius scale, suppose. Okay, and let me tell you, this temperature that I'm marking right now, it is 0 degree Celsius. Okay, 0 degree Celsius. You know what happens at 0 degree Celsius? Everybody knows, I think. Right. What happens at this temperature?
The
Water
temperature is
freezes.
constant, sir.
No. What are you saying? Water becomes
Ice.
Water becomes ice. What is the
Oh,
meaning?
yes, sir.
What is the meaning of temperature become constant? Huh? What are you saying? Jyotirmoy, wake up. Okay, water will become ice at this temperature. Then there's 100 degrees Celsius also, obviously. 100 degrees Celsius, very nice temperature, right? We know what happens here. Tell me what happens.
Water boils.
Water becomes boils or evaporates. Water
becomes
becomes
vapor.
vapor. Yes, that is correct. Okay, so these are 2 temperatures we know. Okay, how they work. Okay, now if I have another scale, right, that is your Fahrenheit scale. Does anybody knows at what temperature in Fahrenheit scale water becomes ice? At what
So
temperature?
32.
Very good, 32 degree Fahrenheit. It's the same thing. Okay, whether I say 0 degree Celsius or whether I say 32 Fahrenheit, they are not 2 different temperatures. They look different, okay, because they are in different scales, but they are same temperatures. Okay, what about 100? How much is 100 then in Fahrenheit?
So 212.
212. Very good. 212 degree Fahrenheit. Okay, this same thing. Okay, 100 degrees Celsius or 212 Fahrenheit. Okay, let me bring another scale which is very important in terms of thermodynamics. Okay, look at this scale. Do you know this? What is this scale called? You've already said
Kelvin.
Kelvin
Okay.
scale. Okay, this Kelvin scale also has another name. Okay, we call it absolute scale. Absolute scale. Please remember this. Okay, and why it's set like that, I'll tell you. Okay, because there is a 0 in Kelvin. Okay, I'll show you where is this. See, the 0 in Kelvin is very below here. This is called 0 Kelvin. Look at this. 0 Kelvin. And how much it is, let me just tell you. Okay, all the scales they have zeros, by the way. Okay. The 0 in the Kelvin scale is like we are talking about minus 273.15 degrees Celsius. So just imagine, what do you think? 0 Kelvin is a temperature or a very low temperature?
Very low.
Very low temperature. Okay, and there's no nothing like anything like negative Kelvin. Okay, you have negative Fahrenheit, you have negative Celsius, but you are not going to talk about negative Kelvin. Okay, this is the starting actually. See, the temperature actually starts from 0 Kelvin actually. Okay, so this is our temperature. The whole idea behind temperature starts from this. Okay, I'll tell you why this 0 is very important. Okay, check. 0 Kelvin is such a low temperature. Okay, it's such a low temperature that all the motion cease to exist. Just imagine such a low temperature that the motion is stopped, completely stopped. And you know what will happen if I go above this, right? Just think now. If I go above, right? Am I talking about 0 Kelvin or higher and higher temperatures?
Higher temperature.
Higher.
Okay, and what do you think?
Higher temperature.
And what do you think now? The atoms or the molecules, they will be at rest, or they'll have slight motion.
Slight move. Slight move.
Slight
motion.
motion will be there. But what is what is the importance of 0 Kelvin? What is important? You cannot imagine anything to be moving at such a low temperature. Can you understand?
Yes.
Okay, so it's such a low temperature that
Yes, sir.
the motion of anything, right, which is at this temperature is going to be completely ceased. Okay, no motion at all. Okay, I hope you understand that point. All right. Okay, now see, can you tell me what's the equivalent of 0 degree Celsius in Kelvin scale?
273.
273.1.
273.15. Yes, Kelvin, very good. That is equivalent to saying 0 degree and so on. Okay, so we have this. Okay, let me write down the formula that is used for conversion. I think in your lower classes also you have learned them. Okay, so if I write a formula, check. Okay, temperature in degree Celsius divided by what? 100. Do you know this formula, guys? Equals to temperature in Fahrenheit scale minus 32 degree divided by 180 and equals to, okay, you have to remember this, temperature in Kelvin scale minus 273.15 by 100. I'll tell you how to use it, okay, but you have to really remember this formula. Okay, so suppose I tell you the temperature in degree Celsius is equal to, let's say, 30 degree Celsius. Okay, and I ask you what is the temperature at Fahrenheit scale. So which two relation you're going to use? You know, you're going to use the first one with the second one. Can you understand? This is a conversion. Can you understand the question, guys?
Yes, sir.
In Celsius scale, what is the temperature? In Celsius scale, what's the temperature? 30 degrees Celsius. So in Fahrenheit scale, what will be the equivalent temperature? So I'm going to use only the first two to get the answer. Okay, so how to do it? I'll quickly show you. In place, I'll write the formulas. Tc by what? 100 equals to what? Tf minus 32 by 180. I'm finding here Tf and I already know Tc. Tc is how much? I told you just now it is given to be 30 degrees Celsius. I can cancel this 0 with this 0. I can cancel this 0 with this 0. And then I can write here 3 equals Tf minus 32 and then divide by 18. Okay. 18 into 3. I don't know. Can you tell me? How much is 18 into 3? Those are good in maths.
54.
54.
Oh, no.
Okay. Yes. No?
Yes.
54. Then equals to what? Tf minus 32. So your Tf, the temperature in the Fahrenheit scale, will be equal to how much? 54 plus 32. Okay, so that is your answer.
80.
That is your, like, how much now? 86 Fahrenheit, degree Fahrenheit. Okay, so I hope you how to use this formula is correct, right? It's clear, right, guys, for all of you?
Yes.
Check. Anybody has doubts here can ask me, huh?
Sir.
I think this formula is clear. Later I'll send you the notes for this. I think I have not sent you, right? Okay, then okay, I'm done talking about this right now. Okay, then let's see. I think we are okay. I have some questions here which I'll give you later. Yeah, I can do that for conversion and all. You can try that. Okay, now see, let's go directly to, I think we can go to your thermal expansion. So thermal expansion is very nice and easy. Okay, and you can just quickly tell me what is thermal expansion, guys. Let's do with only solids first of all. What do you think?
It's expansion of solids
Expansion
or heat.
expansion of solids, yes, because of heat, or in other words, because of change in temperature. Okay, change in temperature. Okay, but you know what, we can also do this. Okay, say if there's an increase of temperature, just imagine the temperature increases. What do you expect from the solids? If the temperature increases, what will change? Expansion means what will change? The length, area, or volume, or all the three?
So all the
All the three. Length is going to increase. Yeah, we know that. Length will increase. Even the area will increase. Even what? Even the volume is going to increase. Okay, if the temperature increases. Okay, even the other way around is correct. Okay, if the temperature decreases, okay, so you can tell me, right? Okay, the length will decrease, the area will decrease, even the volume will decrease. And that's why, you know what, if I take a solid, okay, if I tell you the length of the solid in this topic, okay, it will not make sense, okay, if I don't tell you the what. I have to mention the temperature. At what temperature, what is the length of this object? Okay, if I don't tell you that, then this whole point of thermal expansion does not make sense, okay, because at a different temperature, I think you can understand, right? At a different temperature, will the length be same or it will change? I think you got my point. No, because at a different temperature, what will happen? There will be a different length. So every time I tell you the length, no, I have to always specify what, guys? I have to specify the temperature. Okay, lower temperature, you will see the length has been contracted. Okay, why this happens, I can show you very quickly. Solids, the atoms or molecules are arranged like this, very close to each other. Okay, when the temperature rises, you can easily understand. When the temperature rises, okay, what do you think? They will vibrate or vibrate with more amplitude.
More amplitude.
So they are going to leave their, not leave their mean position, but of course some of them have to leave their mean position. Okay, so they are going to not going to stay in their mean position like that. Okay, but they are going to vibrate and push each other. Okay, so as a result, the whole chain of molecules, right, the number of molecules are obviously not increasing, but they tend to go far away, and you know, right, slowly what will happen if I keep on increasing the temperature? What will happen? Increase it to very high temperature, what will happen? What do you think? It will become a gas, right? That's how anything can become gas, right?
Excuse me, sir.
Yes.
Sir, here solid you are talking about ice, no, sir?
It is not necessary right now. I'm talking about ice. Okay, it is just in general right now.
Oh, okay, sir.
Okay, solid may be aluminum, maybe steel, maybe any metal that you can think about. Okay, any metal, okay, right now. That's how we can talk about this. Okay, but I think you got the point. I think you can understand, right, how temperature brings about motion, right? See, right, they vibrate more vigorously, and they have this gap in between them more and more, so they slowly become gas. Okay, liquid and then gas. Okay, so I think you can understand. Okay, now see, so what is thermal expansion? Let's be also clear with one more thing. If I talk about aluminum, okay, and if I talk about, let's say, steel, let's bring aluminum and steel. Okay, and I have same dimensions. Okay, I took aluminum here, I took steel here. Okay, same dimensions and everything, and you know what, I change the temperature also. Okay, let's change the temperature also, starting from similar conditions. Okay, I change the temperature. What do you think? Aluminum will expand or steel will expand, or they will both expand?
Both will expand.
Both will expand, correct. When the temperature is increased, both will expand, undergo expansion in length, area and volume. Expansion will take place in both of them, but my question is, what do you think? They'll expand by equal amounts or unequal amounts?
Unequal amount.
Unequal.
Very good. Okay, the expansion will be there, but unequal expansion. I think this part is clear, because they are not same, right?
Yes, sir.
Because if I look into the atomic picture or molecular picture of both of them, okay, they are not identical. No chance that they are both are solids, but they are not identical, of course. Okay, the atoms in steel or molecules in steel are different from atoms in aluminum. Okay, so anybody knows who expands, which one expands more? What do you think, steel or aluminum?
Steel.
Okay,
Aluminium.
Let me tell you that. Okay, who expands more?
Aluminium.
Aluminum expands. Okay, expands more compared to what? Compared to steel. Okay, so under similar conditions we have to do this comparison, of course. Okay, so that's not a problem, but at least you understand, right, that some of the solids will expand more, but some of the solids will not expand more. I think you can understand that point at least, right?
Yes, sir.
And that's why, okay,
Yes,
to understand this property, right, we bring three coefficients. Okay, we call it alpha, we call it beta, and we call it gamma. I'll tell you what is that, don't worry, it will be fine. Alpha is called coefficient of linear expansion, it has to do with length. Beta is called coefficient of superficial expansion, it has to do with area, and gamma is called coefficient of volumetric expansion, volume expansion. Okay, it has to do with the expansion of volume. Okay, now think like this. Okay, I'll just go directly with this. Alpha for aluminium, if I tell you it's 0, what does it mean? I'll tell you. What does it mean? What do you think? It means there's a change in temperature, but no
No change in
expansion.
length.
No change in length. Yes, at least you understood that. Very good. Okay, so these numbers are going to tell us that only. Okay, whether there will be expansion or more expansion. So imagine. Okay, I write a number here right now. It's not 0. Okay, don't think it's 0. It is equal to, I'm going to write a value 7 into 10 to the power minus 5 per Kelvin. Okay, that's the value of alpha for aluminium. Don't worry about this right now. Alpha for steel, let me write that also. Okay, it is around 3 into 10 to the power minus 5 per Kelvin. Don't worry, it will make sense in a while, these numbers. Okay, but you can easily understand, right? The number that is your coefficient of linear expansion for aluminium is what? Greater than coefficient of linear expansion for
Steel.
steel. That means aluminium will undergo more expansion in terms of length. And what do you think, guys? Will it only be sorry, I made a wrong number here. Okay, I wrote not alpha, I should have written gamma. Okay, gamma, that is volumetric expansion. Okay, coefficient of volumetric expansion values I'm writing. Okay, not of alpha, huh? But I think you can also understand whose volume will expand more, guys, from here, these numbers.
Aluminium.
Compared to steel. And obviously who will have more expansion in length? Aluminium. Who will have more expansion in area also? It is obviously aluminium. Okay, so don't worry, even for alpha for aluminium and beta for aluminium will be greater than alpha for steel and beta for steel. I think you got this point. Okay, let's quickly talk about very quickly about hard rubber. Okay, hard rubber, what do you think? It will be equal to these two, more than these two, or less than these two? Hard rubber, what do you think?
Less.
I take rubber, we apply change of temperature, we change the temperature of rubber, increase the temperature. Less 2.4 into 10 to the power minus 4. Wait a minute, less or more? Think again. Minus 4.
Sir, it's more.
It's more. Okay, so what does it tells you? Gamma. Okay, gamma for hard rubber, huh? What does it tells you then? The expansion in hard rubber is more or much more?
Much more.
Much more. Okay, the rubber is going
Much
to
more.
expand much more. Okay, compared to steel. Okay, you might be thinking, no, oh, no, maybe this have more expansion, this is more compared to rubber, but no. Okay, this has more expansion compared to both of them. Okay, so aluminium right now in this chart has the lowest amount of expansion that I can talk right now. Okay, I'm done with that. Okay, what do you think, guys? Gold and silver also they expand or not? Gold and silver.
Yes, sir.
Okay, I'm going to write the values of alpha. Okay, no problem. Alpha for gold is around 1.4, and alpha for silver. Okay, silver is around 1.9. So silver expands more. Silver expands more compared to what?
Gold.
Okay, when heated. Okay, so please remember this. It's very nice concept. Okay, now you don't know till now what is alpha. Okay, but to know alpha, I need to come back to one diagram and check whether this makes sense or not. Okay, check. Look at the diagram, then we will understand. Okay, let's say this is our solid. Any solid that you can think of. Okay, aluminium, let it be copper or brass or anything. Okay, iron also, of course. Okay, the length of this solid L. Okay, right now the length of the solid is L, and I have to specify the temperature to you right now. Okay, the temperature right now, okay, is the temperature right now. Okay, the temperature right now is T degrees Celsius or Kelvin if you want to say, no problem. But can you understand this till now? This is a
Yes.
solid. This is a solid. It has certain length, and what's the temperature, guys, right now? T degrees Celsius. Okay, let's add some temperature. Let's add how much? Let's add delta T. Okay, I'm not specifying. So now the temperature is how much, guys? Is T degrees Celsius or more than T degrees Celsius?
More than T.
More than T degree.
More than T degree. Okay, so how much is now? Is T or T plus delta T now?
T
T
plus
plus
delta.
delta T.
And now the new temperature is T plus delta T degrees Celsius. Okay, so now let's check what will happen. Tell me, will it look same? Oops, will it look same or it will look a bit more in length, breadth and height, everything actually. No, let's just talk about length right now, okay, because we are talking about linear expansion right now, huh? So let me just draw that box so it will be clear to you all. See, I've just drawn it, but it is more now, okay, not like before. Okay, okay, now see. So what is this red portion, guys? What do you think? That is what we call expansion, right? This is expansion. Not the whole length is called expansion, okay? This is called expansion, okay? The change in length is called expansion. Now the new length, okay? You can easily tell me what's the new length now, guys? L
L
plus
plus delta
L
L.
plus delta L. This is the new length at a new temperature, okay? So this is how you can think about it, okay? What is delta T and delta L? Let me tell you. Delta T is the change in temperature and delta L is the change in length, okay? If the change in temperature is negative, then what will happen to the change in length also? Negative. Change in temperature negative means the temperature decreases, even the length will contract, okay? That is the meaning of negative delta L. Change in length negative means it decreases, okay? I think you can understand what I'm trying to say here, right, guys? It can be positive also, it can be negative also, no? So that is what I'm trying to say there. I think you got the point, right? What I said here, no? It's clear, this part?
Yeah.
Plus means increase of temperature. That also means increase of length. Minus means decrease of temperature, and then also means decrease of length, okay? So this is what we have, okay? Now we have this theory, okay? Let's just check that, tell me whether it makes sense or not, okay? Say, I'm going to write something and you are going to tell me, huh? The change in length depends directly on what? What do you think? Proportional to what? Look at the diagram and you can think and tell me.
Change in temperature.
Very good. Change in temperature, yes, correct. Think like this. Will there be change in length? Your answer is yes, there can be change in length, depending on whether there is
Change in
temperature or not. Yeah, that is the first thing, okay? Obviously everybody I think understood this point, okay? Then if the temperature rises, then the length will change more and more. If the temperature rises more and more, the length will also change more and more. I think this part is clear. The first one. Check this. Is it okay? The expansion depends on what? The expansion depends on change in temperature, not on temperature, huh? Please be clear, not on temperature but change in temperature, okay? What else? Let's just check, okay? The expansion is also found to depend upon the initial length or the original length. Does it make sense? Is it making sense? Just check. The change in length also depends on what, guys? Original length, okay? What does it mean? Let me just show you. See, if I start with 10 centimeter, okay, solid, and in another case I start with 20 centimeter, okay? Imagine I change the temperature of this by delta T. I change the temperature of this also by delta T. Same material, don't worry about the material, they're same material right now. Now you think, if he is going to undergo expansion, okay, of 0.1 centimeter, agreed with this, right? Check, makes sense, no? Expansion of how much? 0.1. What do you think will happen to this?
0.1.
Yeah, what will happen to this one? Second one. Number 1 and number 2 will also, okay, let's say I have changed by 100 degrees Celsius, okay, the Kelvin or 100 degree Celsius, same thing right now. I've changed the temperature for both of them. I've increased. Here the length has already increased by how much? 0.1. What will you say about the second one? Will that length change or change by 0.1 or more than 0.1? More than, okay, somebody said more than, okay. What about you guys? Think.
0.1.
0.1. Okay, think like this, okay. Here the molecules will push each other, right? Let's say how many molecules are there? 10, suppose. These 10 molecules are going far and far, right? So the gap now between them is extended by how much? 0.1. What do you think? How many molecules are there here?
More than 10.
20 because it's double the length, no? Can you see the diagram? Double, no? I think double than this, no? Okay, so 20, right? Now you think 10 molecules if they are present, no? Same material. 10 molecules when the temperature is changed by 100 Kelvin, okay, produces an expansion of how much? 0.1. That's the gap, right, between these two, right? Extra gap produced by increase of temperature. What will happen with the rest of the 10? Will they just sit like that, or they will also have another expansion of 0.1?
You will have expansion of 0.1.
0.1. So now you tell me total expansion in this case will be what?
0.2.
So now you think and tell me, okay?
0.2.
So now you think and tell me, will the expansion depend on the length or initial length or not?
Yes, sir.
Yes, if you start with a shorter solid, okay, less shorter solid, yes, okay, and you start with a longer solid, okay, which solid will undergo more expansion? Now tell me, the shorter one or the longer one? Longer one. That's why I've written
The
this.
longer
Yeah,
one.
that's why I've written this. Now, does it make sense? Both of them, just check.
Yes, sir.
Okay, yeah. More is the temperature, change in temperature, more will be the change in length. More you start with the initial length, okay, you will have more change of length. That's also makes sense. One last thing, okay, which we have not covered, but now we are going to bring it, okay. I was talking about alpha, beta and gamma, so that is also going to come into picture, and that's how, see how it's going to enter, okay. I'm going to write delta L is proportional to what? Initial length and change in temperature. I'm talking about expansion, okay. One more thing which I did not tell you, but imagine, okay, I take two solids. One is this and the other one is this, which I've already done earlier actually. Same, okay. One is made up of aluminum, you know, right? And other one I took steel. So now you tell me, they have same length, yes. I have changed the temperature by equal amounts, right? I have done that, okay. But what do you think? The expansion delta L in both of them is same or different? Different. And you already know, right? The difference comes because of the length or the change in temperature or because of the material?
Because of the material.
Because of the material, yes. Okay, it's not because of the length. I have taken initial length same in both of them. I have not changed the temperature by different amount. I have changed both of their temperature by same amount, but still, okay, aluminum is going to undergo what? More expansion compared to what? Steel. It is because only one thing, because they are two different materials, okay. But we cannot write, right, in a formula we cannot write delta L depends on material, because material is not a number, okay. So to substitute this material by a number, we bring that constant, and what we have called you that, guys, that constant is called alpha, okay. Alpha delta T, okay. So now you can easily read this formula. See, if the material has higher value of alpha, what does it indicate? It means it will undergo more expansion, okay. Yeah, more change in length or expansion, okay, per unit origin. I can just define to you alpha also right now, very simple. So what's the definition of alpha, guys, from here? Change in length per unit original length per degree change in temperature or rise in temperature. Can you understand? I'm repeating again. What is alpha, guys? Let's write the name first. What is the name, guys? How do you read it? Coefficient of
Linear expansion.
linear expansion. It has to do with what, guys? It has to do with the material of the, it has nothing to do with the temperature of the solid, okay. It has nothing to do with the length of the solid, okay. It has only to do with the material of the solid, okay. Yeah, so alpha we have. Yeah, so can you define to me from this this thing? I think you can understand this part. This is clear, right? I'm going to use this, so be careful, don't forget this. And the rest of the two other things I don't have to teach you properly, you will be fine. Okay, now tell me, guys, what is alpha? Define here. What is alpha? Coefficient of linear expansion of a solid is defined as, read this part.
Change in length
Change
per
in
unit
length,
original
change in length
Original length.
per unit
per
original
unit
length,
change in temperature.
per unit, yes, original length per unit change in temperature, per unit change or rise in temperature, change in temperature, okay. So let me bring that number, okay, for you, and let me just tell you what is exactly it is, okay. See, so let me write alpha for aluminum again, okay. Aluminum, okay, I don't have to do that. Let me just write Al. See, try to understand this, okay. The number that I wrote for aluminum, I think already I did not wrote, right? I wrote for gamma, not for alpha. Now I'm going to write for alpha, okay. That is 2.5 into 10 to the power minus 5 per Kelvin. I will tell you what does it mean, okay. Just be with me. See, it means that aluminum is found to be like this, okay. If I take 1 meter long aluminum wire, I'm repeating again, please concentrate on this, maybe you'll understand. So what is the length of aluminum, guys, right now? 1 meter. Okay, is it okay, guys, for all of you? Check. This is aluminum.
Yes.
We will compare with steel also, okay. If I take 1 meter long aluminum, okay, cylindrical wire, okay, and I change the temperature. Look at the change of temperature per degree. Okay, if you read the definition, it's always going to be measured, right? Alpha, right? Per degree change in temperature. So I'm going to write how much? 1 Kelvin. Can you understand this? That means, did I keep the temperature same or raise? Raise it by how much?
1.
By 1 Kelvin. Okay,
1
let's say
Kelvin.
100 Kelvin became how much? 101 Kelvin. No, so I've changed the temperature. Okay, so we have changed the temperature from 101 10 Kelvin to 100 Kelvin to 101 Kelvin. Okay, then the numbers in front of you, think what will happen. It will remain like this or it will undergo expansion, guys. You already know it will undergo expansion. Okay, and this number here, 2.5 10 to the power minus 5, okay, exactly tells you that is the amount of expansion. Very little, by the way, not so much, okay, because 10 to the power minus 5 is very little, no? So 2.5 into 10, don't think it will expand like anything, okay? But 10 to the power minus 5 meters, what do you think? It's a very big expansion or very small expansion?
Small expansion.
Okay, yeah, it's
Very
going to
small
look, it's going to look
expansion.
like this, see, 0.00025 meters, okay? If I take 1 meter long aluminum and I change the temperature by 1 Kelvin, this will be the change in length of this aluminum. And this number, okay, this number, you can come back again here, see, the amount of change in length in aluminum per unit original length per degree rise in temperature, this number that I've written here, right, which is exactly found by experiments, this is what is known as alpha for aluminum. Can you understand this?
Yes, sir.
Okay, so what is alpha for steel? Alpha for steel means how much steel will change in length per unit original length per degree rise in temperature. Okay, that is the definition of alpha for steel, and the value is, I told you, I'm going to write again. Okay, I don't have the steel number right now, but I can write for some other one. Okay, let me do it for iron. Okay, iron, look at iron. Okay, what do you think? Aluminum expands more or iron? Aluminum, yes. Okay, so iron is 1.2. okay, that was 2.5, but iron is 1.2 into 10 to power minus 5 per Kelvin. But you can understand what does it mean, guys? Yes or no? Tell me what is this number, guys? It means 1.2 into 10 to power minus 5 meters will be the expansion. If I take how many meters of iron, guys? 1 meter long iron, and I change the temperature by how much Kelvin, guys? Per Kelvin. Per Kelvin, yes. Okay, this is how we talk about alpha. Guys, are you really clear with what is alpha? See, they'll ask you a definition of alpha. Your answer is what? Alpha, which is coefficient of linear expansion, is nothing but amount of change in length produced, right, per unit original length per unit change in temperature. Okay, then there's one more thing. Okay, delta L by L. Do you know there's another name that we can call this delta L by L? Anybody knows this one? We call it what, guys?
Fractional change.
Fractional change. We call it fractional change in length. What fraction of the length has been changed? No, what fraction of the original length, right? Okay, so we call it fractional change in length. Okay, so this is also what we can do. Okay, and I think units is very simple, right? Because change in length is measured in meters, length is measured in meters, meters cancel, so 1 by temperature units, right? That is 1 by Kelvin. Okay, so you can write the dimension of alpha also, right? Dimension of alpha will be how much? Okay, temperature we don't have dimensions, so right now I'm not going to write it down, no problem with this. Okay, but at least you know what is the what is that units at least you know. It will be per degree Celsius or it will be per degree Kelvin. Okay, I'm going to ask you a new question now. Okay, not new question, a different something different now. Okay, not different, check. Tell me what is the new length now? New length, what is your answer? The new length is equal to how much? Initial length plus the expansion. Do you agree with this, guys?
Yes, sir.
This is the new length, no, after expansion. Okay, new length after expansion will be original length. There is no formula for original length. Okay, but we know there's a formula for what? Amount of expansion, which we have written just now. If you notice, say this one, expansion depends on what and what and what. This is what we have written, no? Expansion depends on the material, the initial length, and the change in temperature. So I'm going to write alpha L delta T. Okay, so I'm going to write here alpha L and delta T. Okay, because we have this, right? So new length is equal to how much? Tell me what is common in both of them, both the terms. L, right?
L.
So what do I write? 1 plus
1
1
plus
plus
alpha
alpha
delta
delta.
t. Okay, so now let's be clear with this. Are you clear with this formula, guys? The new length will be very high. The new expanded length, right, after expansion will be very high if alpha is what? Very high. I think you can understand that, and this all means that only. Okay, I think we are okay to proceed, right? Is it okay, guys? Did you answer a little bit of it?
Yes, sir.
Yes.
Okay.
Yes, sir.
Can I go directly for your volumetric expansion and superficial expansion? Look at the number
Yes,
2
sir.
one. Okay, for superficial expansion, see how am I writing? Okay, the new area will be equal to how much?
Actual area plus
Actual area
expansion.
plus increase of
Delta.
Increase in area.
increase in area. Now again you tell me, the increase in area, right, which is the expansion of area, right, equals to, depends on what? Depends on initial
Change in
area.
temperature.
Initial area, yes, right. Also depends on
Material.
change in temperature.
Change
Also
in
depends on
temperature.
material. Yes, also depends on material. But this time the constant that will be written will not be
Beta.
called alpha. Yes, it will be called beta a
Beta.
delta t. I think you can understand what am I heading to, right? It's almost the same thing. Okay, so tell me, new area will be equal to what now? Formula a plus
Plus beta
Beta
A
A
delta.
into delta T.
into delta t. So again I can write a dash will be what? A common, so I can write here 1 plus beta delta
Beta
t.
T.
Okay, so yeah, I'm going to use this every time I want to talk about superficial expansion. So new area formula looks like this, where beta, again you can understand, right? Beta for steel will be less compared to beta for aluminum, and that is how it will work. Okay, then tell me, guys, last one, coefficient of volumetric expansion, gamma, right? So how to use this? V dash, let me write directly now. New volume will be equal to initial volume 1 plus
Then plus gamma delta T.
gamma
Gamma
delta
delta
t. Okay, what will be the definition of gamma? You know, it is equal to what? Nothing but what? Change of volume per unit original volume
Actual
per degree
per
change in
Change
temperature.
in temperature.
And what is beta? Change in area per unit original area
original
per
per
degree change in
unit
temperature.
Per
And
unit
alpha,
change in
obviously you know
temperature.
what is that. Okay, change in length per unit original length per degree change in temperature. Okay, so all of them, what do you think? They have different units or same units? They have same units, no?
Yes, sir.
Okay, Kelvin inverse, Kelvin
sir.
inverse, Kelvin inverse. Okay, so they all have same units. Okay, now this alpha, beta and gamma. Okay, what next question they used to ask is this. Okay, obviously numerical they can ask for anything from here, but the next question they may ask you is this. Okay, it is found that this alpha is to beta is to gamma, the ratio, okay, is equal to exactly 1 is to what? 2 is to 3. Have you done this one in your school already?
Yes, sir.
Okay, yes. Okay, so they used to ask, okay, to prove. So I'm telling you already the question, okay, what they can ask, you know. So to prove this one, I'll tell you what does it mean if you are not clear with this. It means like this, say, it means that your beta is double of alpha, that is what it means, okay, and your gamma is how much? 3 times of a alpha value. Can you understand? If alpha is 1, then your beta is twice of 1,
Twice.
and your gamma is thrice of 1, that is your alpha. I think you can understand this one. Okay, the moment I reach till here, no, we have proved that alpha is to what? Beta is to, gamma is nothing but equal to what? 1 is to ratio 2 is to 3. Okay, guys, is it making sense?
Yes, sir.
And I think you can understand why gamma is 3 times of alpha. Can you think? Because gamma is like talking about 1 dimension or 3 dimensions. Gamma is like we are talking about, gamma is like we are talking about expansion in 3 dimensions. Beta is like we are talking about expansion in how many dimensions?
2 dimension.
2 dimensions. So it's double of the expansion in the 1 dimension. That's why this ratio is like that. Okay, so we are going to prove it. Okay, it's very simple proof. I have already sent you a note for that or not, I do not know, right? Okay, let me check very quickly. 1 second, huh? If I have done from that notes, I can do. Yes, let me just check if it's fine or not. 1 second. Where it is downloaded? Downloads. 1 second, huh? I think I can use this one. Okay, I can use this one. Okay, so whatever I've sent, I'm just going to do from there only, so just check. Not good. So I'm going to prove it now. Okay, very simple, so should not be difficult. Just check. Okay. So say, okay, so how to prove it? Okay, first I will prove that beta is twice of alpha. Okay, so how to do it? I'll just take a square plate. This is our derivation. You can check the notes. Okay, if you're confused, I will let you know. Then there's this plate. Let me tell you what is the property. Okay, the temperature of the plate right now is 0 degrees Celsius. That's the temperature right now. I think everybody understands this. Okay, since it's a square plate, it's not 3 dimensional, it's 2 dimensional right now. The temperature, the length, I'm going to call it is L0. Of course the breadth is okay, both are square, no, so same. So these are the sides, okay, L0 and L0. I think this is clear. The square plate has how much length? Side L0, no, that's the side at 0 degrees Celsius. Okay, let's change the temperature. Okay, when I change the temperature, right, it's going to expand, still going to look like a square because it's going to be uniform expansion, of course. Okay, so now what do you think, guys? Is the same temperature or a high temperature? Check. Higher temperature. So I've called the temperature. I've called the temperature to be T degrees Celsius. Is it okay? Just check. Doesn't matter actually. You can take any temperature you want. But I think this is clear, right? Now you tell me, will the length and the side will be same or increased? Increase. So let's call it LT. Okay, and this also let's call it LT. I think you can understand, right?
Yes.
Okay, I'm just going to write one formula. Okay, tell me whether it's clear or not. Tell me the formula for area here. Let's call it A0. I think you are clear with what is A0. A0 represents what, guys? Area at what temperature? 0 degrees Celsius. So what is the area, guys, right now?
L0 square.
L0 square. Very good. Now tell me, what's the area right now, guys? We call it A or AT now?
80.
80. Okay, now tell me. Looking at the diagram, you tell me.
LT square.
LT square. Okay, very simple. Okay, now I only need to write one more formula, that's it. Okay, and then everything is fine. Just check. Tell me, okay, what you have learned just a while ago. New area will be equal to what? Let me write it down. New area will be equal to original area 1 plus
Beta.
Into delta T.
delta T. Very good. And what is the new length? Original length
L plus
One
L1
plus alpha
alpha delta.
delta T. Yes, these are the two things we are going to use and we'll get the answer. Okay, so not to worry at all. Okay, so let's use it properly, but this time. Okay, see, waiting. 80 means new area, so please use this one. New area will be equal to what? Initial area. What is the initial area called, guys, in our case? A0. Yes. 1 plus, let's say the material has how much coefficient? Beta. Same material will not change, the beta will be same, of course. So what do I write, guys? Beta. What does delta T represent, guys?
Change in temperature.
Okay, so change in temperature from 0 to T is how much? T degrees Celsius minus
T.
0 degrees Celsius. It's nothing but T only, right? So I'm just going to write directly T. I think this part is clear. Check. Change in temperature is nothing but T only, no? Final temperature minus initial temperature. So T minus 0. T 0 is nothing. So T only, right? So in place of delta T, I've just written T. Okay, is it okay, guys? Just check.
Yes.
Okay.
Yes,
Okay.
Yes, sir.
Now you tell me. In place of AT, right? What else I can write?
LT square.
LT square equals to A naught. What in place of A naught? What can I write?
L0 square.
L0 square. Yes.
L0
Okay. So
square.
1 plus beta T. Okay. We already have beta in this formula, right? And you know, right? We want to prove relation between alpha and beta. So I need to get alpha. Okay. From where will I get alpha? If I substitute for length or new length?
New length.
New length. Okay, so tell me, what is new length? Your new length is nothing but equal to initial length, which is L0, right, in our case?
L1
Then I should 1 plus alpha delta T is again T.
alpha delta T.
This one is our new length, right? Check, guys.
Yes, sir.
New length is equal to initial length 1 plus alpha delta T. Okay, so this is what I'm using there. Okay, but we have to square it. Okay, we just cannot keep it like that. We have to square it equals to waiting L naught square 1 plus beta T. Okay,
Beta T.
so yeah, let's square it. What will I get? L naught square uh, let's give the bracket 1 plus alpha t whole thing square equals to L naught square 1 plus beta t. Okay, so I'm going to get these two cancelled, so I'm going to get what here? Let's expand this one. 1 plus twice alpha
Twice alpha t
plus alpha square t
Alpha
square
square t square.
equals to 1 plus beta t. Let me cancel
Beta.
1 and 1. We can do that. Now let me just show you something. See, this and this, let's compare. Okay, the first term here, that is has alpha, don't forget that, but the second term in the same side, no, this alpha is alpha or alpha square? Alpha square.
alpha square.
Alpha square. Okay, if you notice there's a plus sign in between. Okay, and just notice something. Do you remember what was the value of the order here? 10 to the power minus 5. Remember this one for aluminum or steel?
Yes, sir.
What will be
Yes,
this?
sir.
What will be alpha square? What do you think? It will be 10 to the power minus 5 or 10 to the power minus 10?
10 to the power minus 10.
Okay,
And
so
minus 10.
what do you think? This alpha square is small or very, very small term?
Very, very small.
Very, very small. It's like writing 0.000025 and adding with what? 0.00000000. I don't know how many I've written. Okay, I'm sorry, I don't know. Okay, but you realize this is small, right? This is like your alpha square, and this is like your alpha. So what do you think? Should we add this to this, or we can just ignore this term?
We can
Ignore.
We can ignore. No need to add, because already this is large, very large. Okay, 10 to the power 5 times larger than that. Okay, that is the effect is going to have the square part, right? So this can be neglected. So what will I get, guys? Twice alpha t will be equal to what?
beta.
Beta.
Beta t, and then t and t gets cancelled. So what have we proved? Twice of alpha is equal to what?
Beta.
Beta.
So we got the first one. Okay, we have proved the first one. I think it made sense, right? Whatever we did. Okay, I think all of you understood. That's why you're still here. Okay, you did not leave the class. Okay, so now let's do the same thing. Okay, let's go to, but now this time which one, guys? We'll go for the last one. Okay, what we have to prove now? We have to prove gamma is how much? 3 times of
Alpha.
3 times of alpha. So how to do it? Not difficult at all. For this case, don't forget, okay, this gamma has to do with volume, right? So I cannot use a square plate anymore. Okay, so I'm going to use a cube, and you can understand again. We go to the same logic. Okay, so what is the length of the cube right now, guys? L0. What is the temperature of the cube right now, guys? 0 degree
0 degrees
Celsius. Okay, now we change the temperature. Yes, Ishita, feeling sleepy? Okay, Ishita's mark is gone now. Okay, now say, then what is the temperature now, guys? Tell me. T degree Celsius. What's the length now of each side now? It's expanded one. Okay, so L T. So now it will have a volume. What will I call it, guys? Volume will be AT, and the initial volume I will call it what, guys? Oh, sorry. Not A. We'll write A or V now. V, no?
VT.
VT and AT. Okay. How much is VT from this diagram? LT cube, right?
LT cube.
And how much is V0 here? L0?
L0 cube.
L0 cube. Okay, now what you have learned from expansion is what? New volume will be equal to initial volume brackets 1 plus gamma delta T, right? I think you have learned this one, right? New volume is equal to initial volume 1 plus gamma delta T. Okay, so you have learned this one, I'm sure. Okay, then now tell me, substitute for 1 by 1. In place of new volume, what are we using? VT equals to initial volume is how much? V0. Yes, 1 plus
1 plus
gamma T.
gamma T.
Okay, now substitute. In place of VT, what can I write?
LT cube.
LT cube. Yes, this is what? V0. L0
L0
cube. Yes, 1 plus gamma T. Okay, now again I need to bring alpha. Okay, because we don't have alpha in this formula, right? So we know that how to bring LT. New length is how much? Initial length 1 plus alpha
Alpha delta T.
delta T. Yes, this is how it's going to enter here. Okay, here you have to enter, see there. So waiting, tell me now, help me out. I have to write L0 cube 1 plus
1 plus
alpha delta T. No need to write. I don't have to write delta T, no? What do I have to write? Let me write again. L0 cube, then we have 1 plus alpha T, yes, equals to L0 cube, yes. Whole thing cube, very good. Okay, I missed that. 1 plus gamma T. Okay, yeah, so you can see already, right? This and this will get cancelled. So now please expand this one. What do I write? A cube plus thrice
Del
Thrice.
Alpha square T square.
alpha square T
Alpha square t, very good, plus thrice
alpha T square
alpha t square plus
alpha T cube
this cube and this cube, no, equals to 1 plus gamma t. Just check. I think it's fine, right? Now you can easily tell me, right, which one is going to be very, very small, guys?
alpha cube
This one will be very small, right? This one, right? Alpha and cube, and then alpha square also, right? Check. Compared to alpha, this will be 10 to the power minus 10. What about this one? 10 to the power minus 5. What about this one? 10 to the power minus 15. So obviously compared to this, okay, these two, this one and this one are very, very small. So this one can be neglected, this one can be neglected. So what do I get here, guys? 1 plus thrice alpha t. Oh, I got square also. We got square.
So the formula is wrong.
The formula is wrong, no?
Yes, sir.
Now what kind of formula is this? Tell me the formula though. Thrice
It will be 1 plus
1
thrice alpha square T square plus
that's
thrice
what
plus alpha cube T cube.
yeah, now Soumitra is saying, okay, after we made all the mess, okay, this is A and this is B, okay, and I was thinking this is A and this is B, no, so I made a mistake, okay, others did not point it out. Now tell me. Yes, A cube plus tell me thrice 1,
Thrice alpha square T square.
so alpha t, no, alpha t plus thrice alpha square t square plus, then now we have
Plus
this one
alpha cube
and this one and t cube, yes, okay, equals to 1 plus gamma t, okay. So we missed it, no, totally, okay. So I think you got the point right now. Where was the mistake, right, guys? Still this will be small, okay, so they can be neglected, and 1 again can be cancelled. 1 minus 1 is 0, so I get 3 alpha t equals to what? Gamma t.
Gamma
also
t
gets cancelled,
t
so alpha
cancelled.
is equal to how much? So 3 alpha is equal to gamma. So earlier we got thrice of alpha equals to what? Beta. See, how can I arrange? No, you must be thinking, right, how it is 1 is to 2 is to 3, no, check. I can write alpha is equal to what? Gamma by 3. I can also write alpha is equal to what? Beta by 2. So these two values are same, no? Both are alpha, right? So alpha is equal to what? Beta by 2 is equal to what? Gamma by 3. So I can divide here by 1. I can write alpha, beta and gamma is nothing but 1 is to 2 is to 3, and they're equal, no? So I think you can understand the ratio, right, guys?
Yes, sir.
Yeah, I think this derivation not a problem. I don't think so. Please check, okay? I've sent you already the notes, huh? Okay, now okay, now okay, I think what you need to do next, you know what, you need to do a numerical, okay? I'll take a break for only 5 minutes. I'll come back, but I'll give you a very easy one, okay? Yes, very easy one I'll give you. Let me just give you this one. I also need to give you the conversion of your oops, not this one, camera. This one. Oh, I've sent you the solution also. Okay, no problem, you can take a break and check the solution also. Okay, let me remove no solution. Yes, very quickly. Don't look. The answer is 3.6 10 to the power minus 6, okay? 3.6 10 to the power minus 6. If you can get it, it's fine. (3.6 10 to the power minus 5), okay? Degree Celsius, per degree Celsius, this one. This is the value of what is the question? Length, no? Coefficient of cubical expansion they have asked. Gamma they have asked, okay? Gamma. But you know something, check. From this, right, they are talking about length. So can you find gamma or you can find alpha, guys?
Alpha.
We can find alpha, right? But you know gamma is how much? Alpha or 3 times of alpha?
3 times of alpha.
So you can use these two information, okay? Find alpha first, then you write gamma is equal to 3 times of alpha, okay? Read the question. Find the coefficient of cubical expansion, means volumetric expansion, okay? Gamma you have to find, huh? So please do it. I'm waiting. Waiting means I'll go roam and come back. Okay, okay, start. Okay, you guys got the answer.
Yes, sir.
Anyone who did not get it? Anyone who did not get it can ask me. Okay, nobody is asking me anything. Okay, fine, say.
Sir,
Yes, Jyotirmoy.
sir,
Yes,
it is written cubical, so means you have to use the formula 3 alpha, no, sir?
Volumetric expansion, yes. The question is coefficient of volumetric expansion. You have to find this. Gamma, no?
Yes, sir.
Okay.
So then put the value of alpha in that formula.
Yes. Alpha, how did you write alpha? Did you understand how to write alpha?
Yes, sir. This
This is the length at 15
L,
degree. How did you write? Check. What's the temperature 1? Temperature 1 is how much? Initial temperature. 15
sir,
degree
is
Celsius,
15
no?
degree.
Okay. Then how did you write? The length 1. L1
So
was right.
minus
L1 is how much? 30 centimeter, no? At this temperature, this is the
Yes.
length, right?
Yes, sir.
Okay, then what is the another temperature?
So then T2 90 degree.
T2 is 90 degrees Celsius, right? What's the length now? L2?
0.027.
No. 30 centimeter plus 0.027. This is the next length, right?
Yes, sir. Yes, sir.
Okay, no problem with that. But what is delta L? Delta L 0.027, no?
27.
Okay.
Yes, sir.
So which one will you? What is the formula for alpha? Tell me. Alpha is equal to how much? Change in length per unit. Original length per degree change in temperature, right?
Temperature. Yes, sir.
So delta L is how much?
Sir.
0.027.
0.27.
Yes, divided by 30, no?
30.
1 divided by how much is the change in temperature? 75, no?
Yes, sir.
75. So this is how you get your alpha, I think. It's clear, no?
Yes, it's clear.
Okay. Then you just multiply this by 3. You get your gamma, okay?
Okay, sir.
Okay. Then what about liquids, guys? Okay, wait a minute. Let's talk about some practical applications of thermal expansion. No, practical expansion. No, not practical expansion. What I said, practical examples. So imagine, okay, you have seen poles and all, right? You have seen poles where you have cables, no? All these are solid cables, of course. Okay, how are cables laid, guys? Do you think the cables are kept like this between the poles, straight?
No.
How are they placed, the cables between the poles or connecting the poles?
Loosely.
They are kept with the slack, they call it, I think, no? Slack. Okay, why can anybody explain why it's kept like that? Yes.
So during cold weathers they will constrict.
Yes, during cold weather the wires will undergo contraction, no? Okay, so the wire will become very stiff like that, okay? And you know what will happen? The whole poles, no, they will, I don't know what is the word, they will be drawn towards each other, right? If the cables are going to contract, no, the poles will, I don't know what's the word, will start bending, right? Okay, I think you can understand, right? If the cables, they contract. Can you understand my diagram? This will happen in cold weather. Did you understand this, guys?
Yes, sir.
Okay.
Yes,
What about railway tracks? You have seen railway tracks, no? There's a big iron piece, there's another big block of iron piece, but there's a gap, right?
Yes, sir.
Okay, because you can understand what will happen in hot days. In hot days, what will happen if there's no gap? If there's no gap, these iron rails, right, will expand. And if there's a gap, there's a room for expansion, right? So no problem, okay? But imagine the gap is not there. We keep the iron rails like that, okay? And now during hot days, what will happen? They'll expand or not?
Expand.
Now they expand, and what will happen? They will buckle up. No, that's the word they use, okay? They will buckle up. So just can you understand my diagram? No, they will buckle up, right? So the train rails, right, will not be straight anymore, okay? So I hope you understand this one also, right? So there's a gap between the rails. Anything else, guys? Any more examples? Can you think about this? Yes. Any more examples? Thermal expansion. Okay, I'll send you this. Okay, then you
Rubber
read.
spacers used in metal framed windows.
Metal frame windows. Tell me, Rajdeep, properly. Yes.
Rubber spacers used in metal framed windows.
These are metal frames, windows. The logic is same. Whatever you're trying to say. No, we place rubber, right? But where do we place the rubber? Maybe here. I don't know where. Okay, but the logic is same. I think you got it. Okay, but the idea is same. Okay, very quickly I'll talk about liquids. Okay, what do you think about liquids? They have expansion or not?
Yes, sir.
Liquids, imagine temperature rises, temperature is increased. Even liquids, they undergo expansion. But there's one problem. Okay, can I talk about linear expansion of liquids?
No, sir.
Doesn't make sense. Liquids, they don't have length, no? So linear expansion doesn't make sense. Okay, what about area expansion? Makes sense or doesn't make sense?
Doesn't make sense.
Doesn't make sense. They don't have proper shape also. Okay, but the only thing is what we can talk about: volumetric. Volumetric expansion, or another name is cubical. No, cubical expansion. That makes sense. Okay, but there are two types of coefficients. Look at this. Try to understand this one. Okay, one is called coefficient of real expansion, and one is called coefficient of apparent expansion. Why two coefficients are there? Let me just help you out with that. Okay, because see, when we talk about expansion of liquids, right, you just cannot talk about liquid. Okay, the liquid always will be present in a what? Yes, liquid container, solid container. Okay, so imagine I have this liquid in this solid container, and you know what, let's increase the temperature. If I increase the temperature, okay, think and tell me, will the volume of liquid expand? Yes, the volume of liquid will expand, but even the volume of what? Volume of container, right? Container is also going to undergo what? Expansion. Okay, so if I take the real, okay, look at this, if I take into account, if I somehow calculated the actual increase in what, if I have somehow calculated what, guys, actual increase or change in volume of this liquid, then the coefficient of expansion, right, the cubical expansion will be called real. Can you understand? And the formula will be what? Change in volume per unit original volume per degree rise in temperature. Can you understand the definition here? Just check, guys. Where this delta V represents what, guys? Change of volume or change of real change of volume?
Real change of volume.
Real change of volume. Okay, and if I measure, okay, if I am not able to measure the real change in volume, okay, but I take into account change of volume of the liquid, but I have forgotten about what? I've totally forgotten about what, guys? Change of volume of the container, and then I calculate the change of volume. In that case, what am I going to write? I'm going to write apparent coefficient of apparent expansion equals to, what is this volume now called, guys? Will I call it real volume of expansion or real change of volume, or I'll call it apparent change of volume?
Apparent change of volume.
Apparent change of volume. That means this one, okay, this is delta V. Try to understand this delta V. Delta V is what? Delta V dash represents apparent
change in volume
change
of the liquid.
Change in volume, yes, of the liquid. Now you think and tell me, does it represent the actual change of the volume of the liquid, or I've not taken into account what when I do this, when I measure this delta V dash, right? I have not taken into account what
Volume, the container.
The change in volume of the container.
of the container, okay, and it is somewhat inside the change of volume of the liquid itself, okay. We have not taken into that, so that in that case, that's why we realize, right? We have how many coefficients now? You tell me. For liquids, we have one coefficient or two coefficients? Two coefficients. One is called coefficient of real expansion, and one is called coefficient of volumetric expansion. Okay. I think you got this idea, right? Is it okay to say okay? Like, are you okay, guys, with this one?
Yes, sir.
Okay.
Yes, sir.
Okay. Then I think for today, I think we can stop here right now. Okay. I do not know whether your teacher has done or not. Anomalous expansion of water is done.
Yes, sir.
Your school has done.
Yes, sir.
Yes, sir.
Anomalous expansion
Yes,
also done. Oh, your school is so good. They do everything, no? So nice. Okay, what about expansion of gases, guys? We'll have 3 of them or only 1 of them? For gases also. Linear expansion, do we talk or no?
No.
No need to talk.
It's
Linear
only
expansion.
volume.
Only volume, yes. Okay, so yeah, right now, just that. Okay. Then what else to tell you, right? Specific heat, I think we can start next day properly. Okay, not tomorrow. Tomorrow I'll not be home. So most probably, let's see Wednesday if I can take. Okay, is it fine? Let's take continuously, okay, because we have lots to finish, no? Otherwise I'll not be able to finish. Okay, so let's do that. Let's try to talk Wednesday at 8. I think it's a very nice time, no? 8 to 9, 9:20, 9:15, like that, no? Tomorrow no. Okay, tomorrow no.
AM or PM?
PM 8 a.m. to who wakes up, no? 8 a.m. You wake up?
Yes, I have to wake up for tuition.
Yes.
Oh, okay. Tuition means what? Online or offline? Sorry, online.
Online.
Online only, na? Yes, we will meet Wednesday. Offline we will not meet. Okay. Who's asking me? I forgot your name, Ray. Giovanna is asking me when will we start the tuition. Giovanna is from which group, Ray? Thursday batch, no? Giovanna, yes. Giovanna, from this Thursday, please talk to your friends also in the group. Okay, so they are very inactive there, so I'm very confused whether they'll come or not. Okay, so you can talk to them. You guys come. If 4 or 5 students also will come, I will take on Thursday. Okay. For Dexway, Biswadeep, you guys, if you want to come Wednesday, okay, I will confirm you guys on Wednesday itself, morning, please remind me.
Okay, sir.
Okay, ठीक है, so bye, thank you. I'll send you some questions, you please do it, so bye, thank you guys.
Bye, sir. Thank you,
Bye,
sir.
bye,
Thank you,
bye,
sir.
bye, thank you.
Thank you, sir.
Thank you.